Hey everybody, let's talk about electrochemical cells here. So you can see the title on the iPad is N36. I do have a set of notes called N36, but I've decided not to use them because they go into a little bit more detail than you really need to, and it usually takes a more than just one class to go through it all, and we don't have that kind of time. So I'm going to go through just the basics today of electrochemical cells. And electrochemical cells are also known as galvanic cells, named after the first person who kind of perfected the technique, Italian chemist by the name of Galvani, kind of 1800s kind of thing. And electrochemical cells are essentially the practical outcome of spontaneous redox reactions that are the transfer of electrons. And an electrochemical cell, very practical thing in that if electrons transfer spontaneously from a reducing agent over to an oxidizing agent, it stands to reason that if that happens spontaneously and electrons can also go through a conductor, that you should be able to separate the two chemicals, and electrons should still be able to transfer between the thing that undergoes oxidation and the chemical that undergoes reduction. And so that principle is kind of where, I guess the motivation to try and develop an electrochemical cell first came from Galvani. And can you use that electrical current that is produced to actually do things for you? And of course, now what has resulted from all of this understanding and engineering related to electrochemical cells is the development of batteries, because the battery is really just an electrochemical cell in a nice kind of neat little efficient package, that we're going to go through the basic principles of an electrochemical cell, and then you'll see kind of what the different parts are, and then logically where batteries come from. Typically in N36 I go through some of the different types of batteries and the rechargeable ones, and how are they designed, and what are the chemicals that are doing the reaction, and what are the actual E cells of those things. And again, we're not going to take that time this year to do all that stuff, so we're just going to go through the basics. So the whole thing's based on the principles of spontaneous redox reactions. So let's start with an example of a spontaneous redox reaction. So a nice simple one is to take a beaker with a 1 molar solution of AgNO3 in it, and into that beaker of AgNO3 you put a nice piece of zinc submerged into that AgNO3. And let me just erase stuff so it looks a little bit more three-dimensional and not invisible. Actually, it looks like a chunk of metal. So if you take a piece of zinc and put it into a solution of silver nitrate, a reaction where you're taking an elemental metal and putting it into a solution of an ionic compound, a single displacement is going to occur. Now I know what the reaction is, so I'll balance it as I'm going. And you will make some solid silver and some zinc nitrate solution. Now, that reaction is really the zinc is going to oxidize and the silver is going to reduce, and the nitrate ions are spectators throughout the thing, just there to balance the charge. And so has a oxidation potential of positive 0.7 And if you actually put a piece of zinc into silver nitrate solution, you'd see the really cool kind of flakes of silver forming on the outside of the zinc, and the zinc would slowly get corroded away and dissolve, and your solution would build up in zinc ion concentration, and your silver concentration would go down. Silver ion concentration would go down. Now, that's not it, other than it being kind of a cool little reaction and you make solid silver, it's not very practical from a producing an electrical current, because the electrons are being transferred where the two atoms are bumping into each other, typical chemical reaction. But if we want to actually use that transfer of electrons for practical purposes, we can actually create a direct current if what we could do is we could separate the zinc from the silver nitrate solution and make the electrons still transfer, but transfer externally through a conductor of some sort, some type of a wire. And so that's where the concept of electrochemical cell comes in. So what would that look like if we took that exact same reaction but made it so that electrons went through parts of the sitting in a solution of its ion. So if my two halves, if up here my two half cell reactions are zinc oxidizing and silver reducing, in each of these beakers what I'm going to have is I'll have a piece of silver sitting in a solution of silver ions, and I'll have a piece of zinc sitting in a. That's how I set the thing up. And over here I would have a big piece of zinc. Oops. Chunk of metal sitting in the beaker. Each of these things, what they're sitting in, so they're a piece of, you take a piece of the metal and you actually put them into 1 molar, to keep them standard, 1 molar solutions of their ions. Now, the zinc nitrate was not one of the reactants, so you might actually say, why do you need the zinc nitrate over there? Well, you're going to see that the movement of ions, whether they're produced or they're being used up, the movement of ions is actually really critical to this whole thing actually being able to work. I'll explain that in just a little minute. So then you've got your two pieces, you've got your two half cells separated, physically separated from each other. But they're set up in such a way that either the silver or the zinc could oxidize, depending on, what's the spontaneous direction going to be. And I will put, I'm going to draw just a little circle in a, because we'll measure the voltage across here. And so this thing is set up now for, you'd think, for a reaction to occur. Well, over here in this beaker, we've already determined what the spontaneous direction is. We've already determined that the zinc is going to oxidize into zinc plus 2, because that's the spontaneous thing to do, while over here in this beaker, silver ions are going to reduce into solid silver. Now, what is actually happening in here is that the zinc ions, or zinc atoms, okay, so if you could go down, to the atomic level, just this. It can't no longer be part of the electrode because as soon as you start making positive things, they'll repel each other. They'll just they'll bing off of there. You can't make a solid out of ions of the same charge. And so that zinc ion is going to go into the water. When it did that, it made 2 electrons. Right? Like that's actually what happened. So the 2 electrons left the zinc atom, and those 2 electrons need to get over to where the silver is reducing. And so what happens is they literally go through the whole system, like through the wire, through the voltmeter, over here. They obviously are going very fast, and they go down the silver electrode down here to where and they would join the silver electrode that is over there. And so what would happen is you'd get, well, it's called plating, and so you would get more solid silver forming on top of that silver electrode, and the mass of the silver electrode would start going up. Over in the right-hand beaker, the zinc electrode is being corroded away into ions, and so its mass would be going down, which should make sense over there. Now, there's a little bit of an issue over here, and before I actually talk about the issue, there's a little bit of terminology I want to make sure that we grasp before we actually move on, because I'm going to start using terms that you need to know what I'm talking about. So these they're not, you don't just use the generic word electrode once you actually know what's happening at each one. At the is the electrode where the oxidation is occurring, and it's always that, and it's kind of a standard. And then the electrode where the reduction is occurring is called the cathode. Now, the few minutes. So you've got like an anode beaker and a cathode beaker, and the anode beaker is where the metal is oxidizing, and over in the cathode, that's where the metal ions are reducing. Now, the issue. Let's go back to the issue here. It seems like all of this should work. It should make logical sense that the zinc is oxidizing, electrons go over to where the silver is, and they reduce. But nature doesn't really like this setup right now, because in this setup right now, over in the anode beaker, where the zinc ions are being produced, the amount of nitrate that's over in that beaker is not changing, and yet you're making zinc ions. And so what happens is over here in this anode beaker is that beaker is getting progressively more and more and more positive as you make more and more zinc ions. Okay, because now they're outnumbering the nitrates. Over in the cathode beaker, the one on the left, because you're using up silver ions, the positive charges are disappearing. They're turning into neutral things, but the nitrates aren't going anywhere. It is getting progressively more and more negative. That's an issue in nature. Nature does not favor processes that are concentrating charge anywhere. If you're trying to make more positive ions in a beaker that's already positive, that is going to be a progressively more and more difficult task. And again, if you're trying to make a beaker already starting to get negative, you're trying to remove positive things and make it even more negative. Again, nature is not going to favor that process. Now, having said that, how do we deal with this? Because this is an issue. It's such an issue, actually, that if you set up the electrochemical cell the way I've got it here on the diagram, it won't actually run. Like if you set this up, nothing will happen. You'll get zero current. No electrons will flow. It doesn't work. So there has to be a way of balancing the charge. And the way that Galvani, anyways, figured out you could balance the charge is allow the positive charges that are building up in one beaker, allow them to migrate over to the other beaker. And the excess negative charges that are building up in the cathode beaker, allow them to migrate over into the other beaker. And so that way, the two solutions had to be connected in such a way where ions could move freely between the two beakers. But electrons wouldn't be able to move freely between the two beakers except through the wire. And so there's a variety of different ways of doing this, but the way that Galvani came up with, and the typical way, you're going to see something known as a salt bridge. And a salt bridge is essentially a curved glass tube, and name in a chem lab, and it's called a U-tube, because it looks like a U flipped upside down. And so a U-tube it's literally a bridge. And what you would do if you're building an electrochemical cell is you set the thing up so that it actually has solution in it. I'm going to use a little bit of color. So I'm going to use, give me some, we'll go with, I'll go with pink. Potassium, I'm going to go with green. So potassium nitrate, and there's a reason why I'm actually using color coding on this. So the salt bridge and it literally acts as a bridge that allows ions to migrate between the two beakers, essentially, to balance the charge. That's the whole point of it. And it's got a solution, essentially an ionic compound in it that is soluble and isn't going to kind of mess up the works in terms of ions that are going to be reactive. It's usually spectator type of ionic compound. But then what you do is in the ends of the actual tube, you actually put some type of a plug in there so that the actual KNO3 solution doesn't pour out and just join the two beakers. So the solution doesn't go anywhere, but it's porous enough that the ions can actually get through that ending. So something as simple as a cotton ball actually works. There's actually porous plugs that are actually made. If you're actually trying to produce an electrochemical cell in a lab, there's actually plugs that'll actually do the job for you. And so what happens is this bridge allows for migration. So which way are ions migrating? That's kind of the last piece of this puzzle. And that's why I use the color coding. So what would happen is wherever you can see that the positive charge is building up in the anode beaker. So positive charge needs to escape that beaker and migrate away out of there. So as soon as zincs are produced, zincs are cations, And what will happen is the cations from that beaker will start to enter the salt bridge. Potassium plus to the cathode beaker. So you will actually get this migration of cations, so the positive ones will migrate out of, and I'll just put a giant plus, out of the anode beaker towards the cathode beaker. And towards, they like literally get attracted towards the cathode, and thus the name of the cathode. So cathode is named that way because cations, the positive ones, migrate towards the cathode. That's why it's called cathode. Anions, and I'll go back to they will migrate towards the anode. Again, anode because anions migrate towards the anode. And so an actual complete electrochemical cell kind of has two major migrations to it. It's got electrons, obviously, going from the anode to the cathode, oxidation to the reduction. But then it's also got the migration of ions to balance charge within the salt bridge, or between the two beakers to keep the whole system neutral. Still up. But what actually happens for a negative charge if you've got a salt bridge there? And so the whole system just kind of remains neutral because electrons are going one direction, but the charge gets balanced by the ions flowing. And you can kind of see that the negative ions are kind of flowing through the salt bridge in the opposite direction. The electrons are flowing through the wire. It's kind of a cool little concept. Now, we already know what the E cells of this thing are, but of course, if you were trying to figure this out, I mean, I already figured them out for you, but this chemical cell would have an initial cell because as soon as the thing starts running and electrons start flowing and we start using up the chemical, the concentration, in particular the Ag+1 ions, it starts to drop. And so as soon as that starts to drop, the potential starts to drop, and eventually your electrochemical cell is going to run out of juice, as it were, and your voltage is going to drop and drop and drop. So this is essentially, I mean, it's the basic gist behind any battery. Any battery system is essentially this. It's got an anode, it's got a cathode, it's got a chemical that is oxidizing, it's got a chemical that's reducing. The two half cells are separated from each other, and it's kind of challenging inside of a battery to prevent chemicals from mixing and yet allowing ions to migrate to balance the charge. And so that's part of the engineering of a battery system, is that. Now, the other thing that you should be able to do is you should be able to kind of dissect an electrochemical cell that's already given to you. So if I give you one, okay, so if I draw one here, we should be able to go through this thing and we should be able to figure out a whole bunch of things about it. We should be able to label it. We should be able to say, you know, what's the anode, what's the cathode, which way are electrons going, which way are cations migrating, which way are anions migrating, and we should be able to tell what is the cell voltage that's being created by this electric cell. Draw an electrochemical cell and then we can analyze it. So you will see that as I'm drawing this thing, one of the interesting features is that you don't need to know what the actual chemicals are if you're going to actually start to draw an electrochemical cell, because the physical structure is always kind of the same setup. You're going to have one beaker with a solution in it, you're going to have a second beaker with a solution in it. You're going to have one beaker with a piece of metal in it, and another beaker with a piece of metal in it. And you know that's going to be the basic setup without even really knowing what the piece of metal is or what the solution is. You are going to have, oh, hang on, got to do my erasing. Make it look like an actual chunk of metal sitting in there. You're going to have your, like a piece of wire connecting the two, and then you are going to have your salt bridge. Just while I'm on the subject of a salt bridge, another way that these things are built is you don't necessarily have to have a salt bridge. Sometimes what happens is you end up with like a porous wall between the two half cell reactions. So the solutions don't mix, but ions can migrate through like a porous wall that's separating the two things. That happens as well. Okay, so you can see that I've got this thing set up. I haven't got a chemical in sight, like I haven't even labeled anything in there. And yet the basic physical setup of an electrochemical cell is kind of a fairly consistent thing. You'll see the same thing all the time. There's a couple of kind of tricky things, and I'll mention them right at the very end, but this is the basic. So for two sodium chloride, concentrated sodium chloride solution. So if that was my situation, I just drew that. I gave you a diagram that looked like that. I'd ask you in which beaker is the oxidation, which beaker is the reduction, where's the anode, where's the cathode, what's the initial cell voltage, which way are the cations migrating, which way are the anions migrating. I get what's happening at the anode, what's happening at the cathode. I could ask a whole bunch of questions about what's happening. To be able to answer any of those questions, the very first thing you have to do is you have to decide what is the spontaneous chemical reaction that's going on here. So the spontaneous chemical reaction that's going on, you have to look at the pieces that are in here. And so over here I've got the chemicals which would be that reduction line on the table. And I'll call that beaker A. I'll call this beaker B so I can, because I don't know which one's cathode and which one's anode yet. And over here I've got the copper ions and solid copper. So what I do is I look at those two things and I wrote them in the form of what's on the table. I may not leave them this way. Obviously one of them is going to have to switch to be an oxidation. So I don't know which one. So what I'm going to do is I'm going to go to the table now. Actually, I think I've got the things already labeled on the table. I do. So I've got the two lines on the table where I've got the copper plus 2 and going to copper and Al plus 3 going to Al. And what I'm doing is I'm trying to decide. I can either have the copper ions reducing and the aluminum oxidizing, or the aluminum ions reducing and the copper oxidizing. So if, and I'll do the blue one as well. Okay, so the black one is copper ions reducing and aluminum oxidizing, and the blue one is aluminum ions reducing and copper oxidizing. Well, which one's the spontaneous combination? Well, as we've learned that if the oxidizing agent is above to the left, that's when the spontaneous reaction is occurring. So you can see that when you set up an electrochemical cell, you set it up in such a way that you've got both possibilities, and you look to see which one is the spontaneous one. So the black one would be the spontaneous one there. So then I go back to my diagram and I say to myself, okay, so the copper was reducing, but the aluminum was oxidizing. So I'm going to actually erase this, and I am going to rewrite it so that the aluminum is oxidizing. Okay. And if I wanted to make those like a balanced overall equation, which you might be asked, of course, I would balance it, and this would end up being 2, 2, that becomes 6 electrons. This will be 3, 6, and 3. And so my actual overall equation is going to be 2 aluminums will react with 3 copper plus 2s, going to 2 aluminum plus 3s and 3 coppers with an E cell of, saw those numbers over there. This was plus 1.66 volts. Is going to have. Now, that's the very first thing you do. Like you go through and figure out what the actual reaction is. Now you can go back to your cell and you can label things and everything else. So remember, the anodes where the oxidation is occurring. So that would be the aluminum one. So the aluminum, piece of aluminum, would be the anode. The piece of copper would be the cathode. So then if you were asked the very specific question, what observation are you making at the cathode? Or what half reaction is occurring at the cathode? Well, the cathode is where the reduction is occurring. So there is my cathode half reaction. What would I physically observe on here? Well, what I would physically observe is I'd see, because copper solid is being formed, I would actually see some, like literally like a layer of brand fresh pure copper being formed on top of it. I would actually have Cu solid, and the word is plating. Pardon me, on top of it. Hold on, I got a cough hard. Okay, I'm back. And then over at the anode, if you were asked for what observation are you seeing at the anode, well, I have a fancy iPad, so I can actually erase this, and I'm going to redraw. I would actually see the aluminum would actually be corroding away. So you would see corrosion of the aluminum. Okay, and it's being chewed up and turning into ions. Okay, and so that's what you would physically see. Now, what about all the the movements of things? Where are electrons going? Where are the anions going? Where are the cations going? So electrons, let's talk about electrons first of all. So electrons, we'll do them in blue, are going to go from where the oxidation is occurring to where the reduction is occurring. And they're going through the wire. They're not going through a solution. They're not going through the salt bridge. So electrons are going to be going through the wire, and they are going to be leaving from the aluminum. They're going to go through the wire, and they're going to be going down the wire, down the copper electrode, which is the cathode, and they're going to go down to where the copper ions are reducing. They jump on the copper ions, they reduce right then and there. So electrons are going from the anode to the cathode, and they always do. They always go from the anode to the cathode. The cations and anions, and I don't know how you want to label this, but what I'll do is I'll do it in purple. you state that, you can write the word, you can draw a diagram, you can say whatever. So what that basically means is the anions are going towards the anode and the cations are going towards the cathode. And any anion that's in the entire system can eventually migrate its way over into the anode. Not all of them. They're not going to all end up in the anode beaker, because they only enough move to balance charge, which doesn't mean all of them. It just means enough to balance the charge. Same thing with the cations. The cations will migrate towards the cathode, but again, not all of them, just enough to actually balance the charge. So what you'll actually start to beaker, this one down, start to show because they're coming out of the salt bridge, and you might even start to see some aluminum plus 3s over here, because they're going to migrate all the way over. Only a few of them, and depending on how long you leave this thing running, they'll actually start to go over there. And I mean, there could be a really tricky type of a scenario where if the aluminum came into that other beaker, maybe it would start to precipitate with some ions, and you might start seeing a precipitation occur. That'd be kind of an interesting scenario. Anyways, so that is the analysis of a electrochemical cell if one's put in front of you, and you kind of go through all the process of what's happening and what would you observe and which way the electrons are going and what's the reaction and everything else. That's how you go about doing it. Now, a couple of little tidbits. Unusual situations is there can be the odd occasion where one of your reactants is in it can't be put into a solid form. Like one of your reactants might be a gas, like it might be hydrogen gas or chlorine gas or something along those lines, in which case that chemical has to be bubbled into the solution, and you can't make an electrode out of chlorine or hydrogen because they're gases. And if that's the case, then oftentimes an inert, so I-N-E-R-T, inert electrode is used. So a piece of carbon is oftentimes used to act as the place where an oxidation or a reduction can occur, even though it's not participating in the actual reaction. The gaseous material would be actually involved in the reaction, but the carbon would act as the physical place where reduction or oxidation could occur. It's an unusual situation. I doubt I'm going to ever ask you that, but you may see it at some future point in your life. Anyways, that's kind of the general gist of electrochemical cells. This principle applies to the engineering of batteries, and all batteries kind of work on this principle in one way, shape, or form, and they have obviously some modern engineering techniques that are used to make a reversible battery. As we've learned, chemical reactions tend to be reversible, and so to reverse this is you would actually put an external power source into the circuit, like where the electrons are flowing, and you would force the electrons to go the other way. So if you could overcome the 2 volts, push the electrons back the other direction, you could force the electrons to jump back onto the aluminum ions and make the aluminum reduce and get the copper to oxidize if you force the electrons to go a certain direction. And that's again the principle of a rechargeable battery. You plug it into the wall and it forces the electrons to go in the reverse direction that they would spontaneously go. You get them to go the opposite direction. Anyways, that's the general gist. So there you go. Now I'm going to get you to try the electrochemical cells practice that you've got, and I'll put up an answer key and we can talk about this upon my return, hopefully next week. Okay, see you all later.